So, welcome to this class. We have been discussing about levels of modeling. And the last class we have seen that gate level modeling. If you want to write a gate level modeling, gate circuit is required. If you want to model a circuit with the help of data flow modeling, we should know Boolean equations. Okay, Boolean behavioral modeling. So for this one, we should know the functional table. We should know functional table, but actually not necessarily a functional table, but different ways are there. But simply we can consider the functional table. Okay. So we have taken that one particular example we have taken that is called full adder that we have taken. We have considered a full adder something like this. Having one input is A, B, CAN, A, B, CAN, and we have an output called S, and we have an output is called Cout. Okay, this is called full adder. Okay, so if you want to understand the internal structure of this full adder for the purpose of behavioral modeling, we have taken a truth table. So what the truth table consisting of? It consisting of A, B, CAN, sum, and Cout, right? And we define that if it is 0, 0, what happened? 0, 0, 1, 0, 0, sorry, 0, 1, 0, 0, 1, 1, 0, sorry. So another combination is 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So if this is the input combination, 0, 0, 0 is the input combination, we expect that the output should be sum 0, carry 0. What about this one? Sum 1, carry 0. For this one, sum 1, carry 0. For this one, sum 0, carry 1. This is again 1, 0. This is 0 and this is 1. This is 0, this is 1. This is 0. This is 0 and this is, sorry. So both are 1, 1, right? So both are 1, 1. Okay, so this is what we should know about the truth table, right? So this information is necessary in order to write a behavioral modeling. Okay, so let us write a behavioral modeling related issue. So as we all of you know that whether you are using the gate level modeling, whether you are using a data flow modeling, whether you are using a behavioral modeling, so the black box connection is the same. That means we treat any digital circuit as a black box, or we can treat that as a module. This module has got input and output externally we can see, right? So if any modeling style you consider, first thing is that external input for the any modeling style is the same, right? So in that perspective, we have started off writing the behavioral modeling is something like this. So module is the keyword that we have to use. What is the name of the module we have started? FA. So what are the input signals here is A, B, CAN, sum, and Cout. So these are the variables I'm using. Now out of all these things, what are the inputs here is now? Is that inputs are A, B, CAN, right? So what are the outputs here is that outputs are S comma, sorry, I'll write another color, S comma Cout. Fine. So far so good. And finally, I'll write N module. For the sake of simplicity, I'm writing here is the N module. Okay. So now this is what essential for any modeling style. External view for any modeling style is the same, and this is the skeleton for your program. Now, so what we have to write here, so that is depending upon how we look at the digital circuit, digital internal circuit is. So we can use so far we have seen a gate level circuit. So far we have seen Boolean equations we have seen. Now we are going to look at the table. Okay. So now how do we write this table in this particular internal view? Actually, user-defined primitives are there, but we don't talk about that right now. We focus mainly on this table. How do we incorporate this table into your program? For that one, I'm going to use one statement called always statement. Always statement I should use. Okay. Always at the rate of some sensitivity list I need to write. Okay. And then I should start, begin, and end. So this is what it is necessary for the behavioral modeling. Whenever you are writing the behavioral modeling, so this particular information is necessary. Okay. Always at the rate of some sensitivity variables that we have to write, and then we need to start, begin, and end. Here we need to write the procedural statements. Okay, so in the previous class we have seen what are the statements we use in gate level modeling. As all of you know that gate primitive statements we used. Similarly, what are the statements we used in behavioral data flow modeling? So continuous assignment statements we have used. Similarly, in the behavioral modeling, what are the statements we should use here? Procedural statement we should use. Is it clear? Now, so if you want to write a procedural statement, here we should know what are the procedural statements available in Verilog HDL. Okay, so the procedural statements are, the one thing is if statement I can use. The second one is if else statement I can use. The third one is case statement I can use. Fourth is for loop I can use. So fifth one is while loop I can use, etc. But essentially we use if else and case and for loop only. Okay, that means these statements I think you have seen in the C language. Okay, so the behavioral modeling is similar to that of C language, but no need to focus more detailed about the C language related issues here. Very easily we can understand these concepts with respect to the hardware design. Okay, so these are the procedural statement we have to write it here. Okay, so let us write this. Let us consider for the sake of simplicity, I'm using the case statement. In order to write this truth table. Okay, for the simplicity, I'm using the case statement. When time comes, I will discuss about if and if else and for loop and everything. Okay, fine. So I'm going to copy this. Copy. I want to paste it here. I'm using the same program here. So if you want to write this one, we should understand this one also. This table is also required. Okay, fine. See here, one important point that we should remember here. So we have started off using the always statement, right? We are using here is the always statement. So let us think about what do you mean by always statement. So always statement says that whatever the statements that you write, whatever the statements that you are writing between the begin and end, between the begin and end, these statements are executed all the time. But we say that all the time means it is endless loop. Okay, endlessly we are asking that we have to do this one. But this task has to be performed based on at the rate of symbol. So this particular process, the procedural statements must be executed whenever there is a change in a particular variable. Okay, so that means, so these procedural statements must be executed whenever there is a change in some variable. Okay, so what variable we need to consider so that we need to execute procedural statements, right? So normally we consider input variables. So here is input A and B and C. So whenever there is a change in A, or whenever there is a change in B, or whenever there is a change in CAN, this particular block must be executed. Why? Because ఎందుకు మనం అది execute చేయాలనుకుంటున్నాం అంటే, for example, look at here. So when the inputs are changing from A to something like this is a one combination to another combination. So we are changing the input of CAN. If you move from one particular input combination to another particular input combination. See, in that situation, we can observe that we can find a change in sum. Okay, so therefore, whenever the input is changing from one value to another value, the output is also changing. That change of output we need to execute. Okay, so that is the reason why we need to consider the input variable changes in order to find out the output. Okay, if you want to find out the output change, we need to identify where the input changes are occur. So that's the reason why I am going to consider the inputs are A, B, C, N. So whenever there is a change in A, the following begin and end block must be executed. Whenever B changes, the following begin and end statement must be executed. Whenever CN changes, following begin and end statement must be executed. Or otherwise, all the three cases is changing. For example, look at here. So in the first case, what we observe that first one, so only C is changing. So therefore the loop will be executed. So that means always statement will be executed. What about here? B and C are changing. So this is from B 0 to 1, C and 1 to 0. So again, we see only change is observed at CN only at this point. But here, A is changing, B is changing, C is also changing, right? Similarly, if you consider here only CN is changing. Okay, here you can consider CN changing and B is also changing. Here, if you consider only C is changing, that means throughout this truth table, we can identify that either A can change, A can changes here, A can change, C can change, or B can change, or altogether can change. So whenever there is a changes that is observed in the truth table, that change we need to notice here. So that change we can call it as sensitivity list. What we can call it as, this is nothing but a sensitivity list. Sensitivity list. So we are telling to the simulator that the changes of the sensitivity list we are talking about. The change of the A or changes of B, changes of the CN. That's what we are talking about at the rate symbol says that. I hope everyone can understand this point, right? So therefore, whenever you are writing the behavioral modeling, always at the rate of sensitivity list, we should present, we should produce. Clear? I hope everyone can understand that point. Okay, now, so here we need to write a procedural statement, right? So for the sake of simplicity, I'm using the case statement, right? So sorry, I'm using the case statement. How do we use the case statement? So the case statement is something like this. So case is the symbol I have to use. Case is a keyword. Small letters only I have to consider. So each and every input, I am going to consider it as one case. This is one case. So this is the second case, right? So this is the third case. This is the fourth case. This is the fifth case. Okay. This is the sixth case, seventh case, eighth case, right? So these are the 8 cases are present in your truth table, right? So actually individually we have A signal, we have individual B signal, we have individual C signal. Okay, I cannot write a case A comma B comma C and I should not write like this. Instead, individual signals are combined with respect to concatenated symbol. So this information we will discuss more detailed when coming to the behavioral modeling. Just what I'm saying that here I have a 3 input signals are individually present here. So I have individual 3 input signals are present A, B, C. I am treating all this information, individual information as a single data. I am considered as a single data of size is 3, for example. So in that situation, I'm going to use the concatenation of 3 variables. So here is A, B, C, for example. So if you write A comma B comma C concatenation symbol, this is the curly brackets we have to use. So if you're using the concatenation of A, B, C, it treated as a single line. It treated as a single line. Okay. Therefore, it is possible to write the statement is something like this. Okay. So now A is 1 bit size, B is also 1 bit size, CN is also 1 bit size. So when we combine these 3 1 bit sizes, what is the final size of the A, B, C, N? Everybody knows that 3 bit size, right? 3 bit. So 3 bit of 0, 0, 0 is the 3 bit of 0, 0, 0 is the one case. So for numbers, so this is the one number, 0, 0, 0 is the one number. That number is represented by, in Verilog point of view, 3 digits that we are using. Its format is binary format. Its value is equal to 0, 0, 0. That's what it says that. If that is the case, so what it has to produce here? It has to produce some signal is equal to 1 bit of 0, comma, Cout is equal to 1 bit of 0. Is it clear? What I'm doing is nothing is there. Just only, you just understand. The first point is if A is equal to 0, B is equal to 0, C is equal to 0, sum must be 0, carry must be 0. So that's what I'm writing. But instead of writing directly 0 here, so number format I'm using. So what is the number format? How do we use for the different formats? We will see in the coming classes. Okay. So S is equal to 1 bit of 0. Cout is equal to 1 bit of 0. Okay. So as all of you know that in the C language, true statements, if you are writing, then we have to use the curly brackets. But in this particular Verilog point of view, we are writing this one as curly brackets that we have to use. But here in Verilog point of view, we should use begin and end. Okay. So I think better I should move this one to somewhat this side. So it is a begin. It is a begin and end. Instead of writing the brackets, we are writing begin and end. Is it clear to all of you how I have written the first statement? Is it clear?
Yes, sir.
Somebody write in the chat box how I have written a case statement for one particular combination. Okay. Shall we write the second statement? What is the second statement says that? Yeah, thank you. So second statement is 3 bit of 0, 0, 1. So that is the second case statement. Okay. Now begin and end is the keywords. Begin and end we have to use. There is no semicolon at the end. Okay. And we need to write, what about the sum signal here? What is this here? 1 bit of 1. Clear? Cout is equal to 1 bit of 0. Right. I hope everyone can understand this one, right? There is no difficulty in it. Just we have a truth table. The contents in the truth table we are treating as a one particular combination we are treating as a case. So we have to mention one case and we should say that if this is the case, this should be the output. Okay. Similarly, we can write for all the combination. 8 combinations are there, right? So we need to write all the 8 combinations, 0, 0, 1, 0. Okay. I think it's better to copy this one 8 times. Copy. I want to write it in 8 times. So this is the one. You keep this one aside. I want to use this one for multiple times. Okay, how many are there now? Yes, I should remove this one first of all. Okay, so what is the next one? So instead of that is this should be removed. This should be 1, 0. What about the next one? 0, 1, 1. What about the next one? What about the next one? 1, 0, 0. Okay. What is the next one? This is 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay. Okay, fine. Well, I need to mention the outputs also. What are the outputs here? I should mention the outputs at these places. Right. What is the output? Can anybody help me? So for the 0, 1, 0, what is the output? So 0, 1, 0, for 0, 1, 0, someone carries 0. Someone carries 0. Someone carries 0. What about here? Someone, sorry, some 0 carry 1. What about the next one? Let us begin here. Let us begin here. Some value is equal to 1 bit of 1. Cout is equal to 1 bit of 0. So finally, I need to write and here. Similarly, what about here? Sum is 0, carries 1. 1 bit of 1. What about here? Sum is 0, carry is equal to 1. Lastly, begin. So S is equal to, sorry. So for simple circuit, it looked like very difficult to write all these things. Okay, when complicated circuits are there, behavioral modeling is only the best choice. Okay, you will notice that one later on. For the simple circuit, you feel that it is more complex than whatever we have seen so far, but it's not true. Okay, one. Finally, we need to write end. Okay. So another important point we have to write, don't forget about this one, default statement I need to write. So for this one, begin, and I need to write for default S value is something else. I'll put S is equal to all zeros. Okay, Cout is also a 0. So this detailed discussion we will see later on. Finally, we need to write end case. Okay, finally we need to write. So this end case is meant for this end here we have case we have written. So that case we are ending at this point. Okay, and we have started off using the begin. So for the begin, I need to write end here. So for the begin, I need to write end here. So finally, I need to end the module, end module. I hope everyone understood this point. Okay, so for your sake, I'm reducing the size. So this is how we need to write. See, so only the thing is that the case is one of the procedural statement that we have used. Okay, either if statement also we can use, for loop also we can use. So many ways we can do it. Okay, So therefore, please remember this point. Okay. So this is how we can write the behavioral modeling for a full adder. Okay, so far we have seen that how to write a Verilog program for the full adder using the gate level modeling, data flow modeling, and behavioral modeling. Okay, so for the first time, we feel that the data flow modeling is a very simplest one. As the complexity increases, gate level modeling as well as the data flow modeling is a complicated to write, but at a tedious job. I can say that it's easy, but tedious job. But if you use the behavioral modeling, whatever the complicated circuit it is, we can easily write this one with the help of behavioral modeling, right? So is it clear to all of you? How do we write a behavioral modeling?
Yes, sir.
Please write in the chat box. Is it clear to all of you? So how do we write a Verilog program in the data flow modeling? Sorry, gate level modeling, data flow modeling, and behavioral modeling. Okay, so we are going to talk about in detail discussion about each and every module in every modeling style in the coming chapters. But this is the overview of the entire programming style. Okay, fine. Thank you very much for giving this response. And let us see. I think this will be very visualization is good. Okay. Now, so far, so good. What we have done so far, what we have done so far. So far, we have seen that, for example, if we have a digital circuit, we have a digital circuit, right? Digital circuit. Not a digital communication, it's a digital circuit. Okay. So what we have done with the help of HDL, we have described this particular digital circuit, right? So in different ways I have described. Okay, not necessary that each and every, not necessary that one particular digital circuit I have to describe in 3 ways, not necessary. So depending upon your application, whichever is the simplest one, we can use that one, fine. Now, what is our responsibility is that once we have a HDL program, we have to give it to synthesis simulation tool. Okay, once we have a HDL code, okay, that code must be simulated. We must simulate the code, right? Sorry. I think it's of the digital circuit. Whatever the digital circuit is there, the digital circuit must be verified functionally. What do you mean by the functional verification of your digital circuit? Which means that if you give A input signal to the digital circuit, B input signal, C input signals to the digital circuit, it should produce sum and carry according to your truth table. So that is the process is called simulation. Okay, verify the functionality of the digital circuit is called a simulation, as simple as that. Okay, the simulation is done by the CAD tool. Okay, so therefore that is required. So what we will get finally? So output waveforms that we will get. We will get output waveforms, or according to the truth table, text information we will get that one. So we will get text information like a truth table fashion. Text information also we can get. Text format also can be possible. Okay, outcome of the simulator we will see later on. So if you want to verify your HDL program, whether you have described it correctly or not, we have to give this HDL code to the simulator. Okay, simulator will simulate your code by applying different input signals A and B and C signals to the circuit, and it will produce an output. Just you have to compare your digital output waveform or of text format to your truth table. So truth table of your digital circuit. So truth table of your digital circuit, it will compare. So if both are same, whatever you have designed, whatever you have described, that is correct. Otherwise your description is not correct. Okay, so the question is, another question is that how do we simulate? How do we simulate your circuit? So that's the question. So the answer for this question is that if you want to verify your circuitry, if you want to verify your HDL code, if you want to verify your HDL code, what we have to do is that, or I can say that I should not write like this, the simulator. So we need to have a HDL code. HDL code is required. We need to have an HDL code. And apart from this one, we need to have test vectors also, test bench also, or text vectors. We have to give the test vectors to the simulator again. What do you mean by that one? For example, you considered this is a full adder, right? So somehow we have given input A, B, C, and you are getting output is sum and carry, right? So no problem. So we have described something like this. If you want to verify, suppose A here you given B, C, N, and S and C out, right? So somehow we have described this one. Fine, there is no issues at all. But if you want to verify this full adder, what do you mean by the A? A ante enti ikkada manaki? What do you mean by the B? What do you mean by the C? Sorry, these things are not properly connected. What do you mean by the A and B and C? That means it is that is externally we have to give some kind of waveforms, right? Suppose A is equal to 0, B is equal to 0, something like this waveform fashion that we are giving A and B. B is also electrical signal, we are giving A to the B, something like this. C is also we are giving something like this. Okay, so we are giving some external signals, electrical signals like for A and B and C and or binary information we are giving at the input of the full adder. Okay, so therefore this description also is required. So this is called test bench. This is called test bench. When A is equal to 0, when B is equal to 0, when C is equal to 0, we should mention in the form of a waveform. Or when A is equal to 1, when B is equal to 0, when C is equal to 1, like this we have to write. So that is called a test bench waveform. So unless otherwise, if you're not giving the A, B, C, N values externally to the full adder, the simulator is not able to simulate your design. అర్థమైందా? హెచ్డిఎల్ ఏం చెప్తుంది, నాకు ఏ ఇన్పుట్ ఉంది, బి ఇన్పుట్ ఉంది, సి ఇన్పుట్ ఉంది చెప్పింది హెచ్డిఎల్. మరి టెస్ట్ బెంచ్ ఏం చేస్తుంది, అట్లయితే ఏ ఎప్పుడు ఏ ఈజ్ ఈక్వల్ టు 0 పలానా టైంలో, బి ఈజ్ ఈక్వల్ టు 0 పలానా టైంలో, సి ఈజ్ ఈక్వల్ టు 1 పలానా టైంలో. సో దట్ ఈస్ హౌ ద టెస్ట్ బెంచ్ హ్యావ్ టు గివ్ ద ఇన్ఫర్మేషన్ టు ద A, for the B, for the C. The simulator will take this input test bench information, okay, and it will produce, what do you mean by the, how do we produce the sum and carry? It will produce sum and carry. Is it clear to all of you? What is the simulator responsibility? Simulator will take the HDL code and simulator will take the test bench waveform, what are the necessary input signal values, and apply this input signal values to the design, and it will produce the sum and carry, C out. That is what the responsibility of the simulator. Okay, so or simply I can say something like this. So another way that I'm going to tell you, for example, we have a Verilog code. Here we have a Verilog code. Verilog code for the full adder is given. Okay, what it says that? It says that A input signal is available, B input signal is available, C input signal is available. So what it has to produce, some signal it should produce, carry signal it should produce, right? So therefore, what the simulator will do is that, so this is what the simulator is. So this is what simulator environment, for example. I can say that simulator environment. Simulator. Oh. Sorry, just wait for a second. It's unexpectedly, it is closed. Okay, it is called simulator environment. Okay, so in this simulator environment, we bring that code. Okay, and we are giving some test bench waveforms to this one. A ki em chestamante manam a is equal to 0, b is equal to 0, c 0. A is one, suppose a, b, c. Something like this waveform, the information we are giving in this way. Okay, so what the simulator will do, simulator will take this input signal. So a is 0, b is 0, c is 0. Okay, and apply this one into the code. What is the code that is available? So here something like this we have written the code. Okay, here we have written the code. So it puts a is equal to 0, b is equal to 0, c is equal to 0. And it will produce, when this is the true, if this condition is satisfied, then automatically it will give sum is equal to 0, carry is equal to 0. Therefore, it will produce an output signal for this one is, this produces some output signal is sum is 0, carry is 0. I hope you have an understanding. Okay, so therefore again, once we are giving this one 0, 0, 1 you have given. So again, it will go to the code and assigns its input value to the 0, 0, 1. And for that particular combination, what is the output we have described, that output will be produced. Sum is equal to 1, carry is equal to 0. So that is how the simulation will be performed when we give the HDL code as well as test bench waveform. Is it clear to all of you? Okay, this is what the topic of the discussion in the next class. So the next class we are going to look at how do we writing test bench. Writing test bench. How do we write a test bench for input A, for input B, for input C? Okay, so this is what we will discuss in the next class. With this, we stop discussing about the behavioral modeling. Okay, in fact, the test bench is common for all the three modeling styles. So that topic we will, the topic we will discuss in the next class. Thank you very much. If you have any doubt, please send me a mail, or you can send it through the WhatsApp also. I can clarify your doubts. Okay, so we stop here today. We will see in the next class. Thank you, one and all.